sine 48 cos 17 minus cos 48 sine 17. So I go and I look at my identities and I try to see which one goes sine cos subtract cosine. Okay, so I look at my identity sheet, and does anybody see like the difference identities? Yeah, sine A minus B. Do you see that one? That follows that pattern. So sine A minus B, just meaning this is your A, this is your B. Okay, so we'll write it as sine 48 subtract 17. And sine 48 subtract 17 is what? Sine 31. Okay, B, we want to simplify this. So we have cos squared pi over 3 minus sine squared pi over 3. So we look in our identities that we just wrote down. Is there anything that's cos squared minus sine squared? Okay, cos 2a. A being our pi over 3. So it's actually cos 2 pi over 3. And so we might as well times the 2 in there. So you can write it as cos 2 pi over 3. So let's turn to example 2. And that's on page 302. And it says determine the alternate forms of double angle identities for cos. Okay, so since we already wrote them all down, we have them. Okay, but this is if you were trying to find it. Okay, and by find it, I mean solve for it. You have it on your sheet, but this is if you were solving for that part. So it says determine an identity for cos 2a that contains only the sine ratio. Okay, so it only has sine. So if you were looking at cos 2a, you'll notice on your sheet, oh, that only has a cosine ratio, sorry. If you're looking at your sheet, cos 2a has like 3 options, and they're looking for the one that only has cos in it. Okay, so what does that one look like? 2 cos squared a minus 1, right? Okay, so if we had that on the sheet, that would be our answer. Okay, but I'll show you how they come to the inclusion. Okay, so they're saying cos 2a, if you only had this first one, say you only had this one, it's got cos and sine in it, and we only wanted to have cos in it. Okay, so that means we have to do something to get rid of this sine piece. Okay, so if we remember back, do you remember the Pythagorean identity? That was cos squared plus sine squared is equal to 1. Okay, so if we subtracted the cos squared over here, we would have sine squared is equal to 1 minus cos squared. Okay, so they're saying that sine squared is the same thing as 1 minus cos squared. Okay, so that means we could replace this sine squared right here with this instead. Okay, so we could replace our sine squared from here, and we could put 1 minus cos squared instead. So our equation, oh, that's a 2, sorry. We had cos squared a and a subtraction, and instead of sine squared, I'm going to put 1 minus cos squared. And I should probably put an a. So to finish this off, we have a cos squared a, and we have, sorry, this should be in brackets, remember, because that negative needs to go here and there. Okay? So if I multiplied into the brackets, I have a minus 1, and this minus and a minus turn into a plus cos squared a. So you'll notice now we have a cos squared a and a cos squared a. So we have 2 of them. So we have 2 cos squared a minus 1, which is the answer that we found on our identity sheet 10 minutes ago. Okay, let's cruise to example 3 in our textbook, still on page 302. Okay, so it's saying consider this expression. So we have minus cos 2x over sine 2x. They're saying, what are the non-permissible values? This is the part that we do not like totally, but we're getting there. Okay, so let's look at the bottom. We don't want the bottom to equal 0, correct? So let's look at what sine 2x is. So if you look at your double angle identities on your sheet, what is sine 2x? It's, what was that, sorry? Okay, so it's 2 sine, we can say a or x, cos x. Okay, so that's really what the bottom is. Sine 2x is the same thing as 2 sine x cos x, according to our identities. So we have a sine and a cos, and if any of those equals 0, then we're in trouble. Okay, so on our unit circle again, where does sine equals 0? At pi. Okay, so that's bad. And then cos is at where? At a half. Okay, so basically we can't have it at pi and a half, a pi, like every half a pi is bad, right? So our non-permissible value, whoops, sorry, it should be half pi n, meaning if n was 1, then it's half pi. If n was 2, then that's a full pi. 3 would be 3.5 pi. Okay, so that's our non-permissible value. Now we get to simplify this expression to one of the 3 primary trig functions. So we're trying to break it so that it's as simple as it possibly can be. Okay, so this was the part that I said I liked the most. So we already switched the bottom. So we can write the bottom as 2 sine x cos x, because that's the same thing as sine 2x. Okay, and what can we change the top to? Even piece of the top. What about this guy there? Cos 2x. Can we rewrite him as something? Lots of things, right? Is there one with sine in it so that maybe we can cross something off from the top and the bottom? Okay. How about, is there one with a 1 so that we can think about maybe getting rid of that too? 1 minus 2 sine squared, and I'll put x because I started with x there. And we still have this 1 in front, right? Okay, so all I did was I replaced this cos 2x with this guy. Okay, so remember this negative goes in to the bracket. So it would be we have a 1 out front, and a minus times a 1 is a minus 1, and a minus times a minus is a positive 2 sine squared x, and we still have our bottom 2 sine x cos x. Okay, so this doesn't look a whole lot simpler, but hopefully we can get rid of some stuff. So this 1 minus 1 is 0, right? So that's gone. Okay, what about this 2 and this 2? It can go. And this means we have like 2 signs in the top, like a sine and a sine. And we have a sine in the bottom. Okay, so this sine squared, he's actually like a sine x and a sine x. And we have one of them there. So now all we really have is a sine x over a cos x, because he's still in the bottom. And what is sine over cos? In our, yeah, tan. Okay, so let's look at example 4. It says determine, anybody see this, exact values for each expression. Anybody remember what exact values means? And we have, how do we find exact values? Okay, and how does this go again? 1, 2 and root 3. And then our other one is 45, 45, and it's 1, 1 and root 2. Okay, special triangles give us exact values. Okay, so we can use the unit circle too, but we can use special triangles also, right? And it says determine the exact value of this, okay? When I see the radians, it's easiest if you look at them as a degree, I always think. You can work through it as a radian, but if we switch them to a degree, it might be easier. Okay, so remember, switching a radian to a degree, you multiply by 180 over pi. So the pi's cross off, and you have 180 divided by 12, which gives you 15 degrees. Okay, so what this 15 degrees means is we have to find the exact value, and what we're going to use is our sum identities or difference identities. Like when we're talking exact values, we have to have 30, 60, or 45 for angles, right? So is there any way we can make a 15 out of those angles that are shown on the special triangle? What's that? Well, we're not going to times. What if we're using subtraction or addition? How could we make a 15 out of those special triangles? 60 minus 45. Okay, 60 minus 45, or you could do 30 plus. No, we can't. We got to do 60 minus 45, right? Because sine 15 is the same thing as sine 60 minus 45, because 60 minus 45 is 15. Okay, so if we're doing sine 60 minus 45, which one of our identities is that, and what pattern does it follow? So it's got a subtraction, so it's probably a difference identity. And so is it sine A minus B then? Okay, so we'll say this is A and this is B. So then to finish the pattern, sine A minus B is equal to sine A cos B, subtract cos A sine B. Okay, so then all you do is fill in your A's and B's with the appropriate angle. So A is 60, B is 45. Oh. Okay, so then now we need to know what sine 60 is. And yeah, you could go on your calculator and get a decimal, but that's not an exact value. So sine 60 is opposite and hypotenuse. It's root 3 over 2. And that's times into cos 45. So 45 cos is adjacent over hypotenuse. So 1 over root 2. Subtracting cos 60 is adjacent over hypotenuse, which is 1/2. And sine 45 is opposite and hypotenuse, which is 1 over root 2. Okay, these should be simplified first, rationalized, because we do not like having that root in the bottom, remember. So I'm going to leave this guy, and I'm multiplying him by root 2 and root 2 because we don't want the root in the bottom. What's that? No, because it's going to turn into a subtraction question, right? So this turns into root 2 over 2, and same with this guy. He'll be root 2 over 2. Okay, so now when we multiply these guys together, we have a root 3 times a root 2 is root 6, and 2 times 2 is 4. And then it's going to subtract these two multiplied together. So 1 times root 2 is root 2, and 2 times 2 is 4.